management information systems, databases, SQL, and data analytics. Take a breath. This review is designed to lock the material in. Section 1. Business transactions and POS systems. Modern business begins with transactions. The first modern transaction processing system was the cash register. Its purpose was accountability, reducing theft and standardizing sales. Today, that idea evolved into the point-of-sale system, or POS. A modern POS integrates many devices: barcode scanners, scales, touchscreens, MICR check readers, credit and debit card readers, tactile keypads for accessibility, cameras, and RFID readers. This means transactions are captured faster, with more detail, and with fewer errors. The first company to use a mobile POS was McDonald's. Square incorporated change payments by creating the first credit and debit card reader that connected directly to mobile devices like smartphones and tablets. Key idea: transactions create data, and data must be managed. Section 2. Databases and DBMS. A database is a collection of organized data, tables, relationships, and metadata. A DBMS, or database management system, is the software that creates, processes, and administers the database. Major DBMS vendors include Oracle, Microsoft, and IBM. Using a DBMS solves three major problems found in traditional file systems: data redundancy, duplicated data wastes space and slows access; data inconsistency, multiple copies don't always match; data security, permissions and access rights protect data. Remember this distinction: database equals data, DBMS equals software that manages the data. Section 3. SQL, queries, forms, and reports. To interact with a database, businesses use SQL, structured query language. SQL is the standard language for relational databases. SQL is used to retrieve data, update data, add data, delete data, generate reports. A query is a question asked of the database using SQL. Queries allow users to filter records, find exact data quickly, summarize information, automate tasks. Forms are used to input and view data. Reports are used to present formatted, summarized, printable information. Section 4. ERDs and database design. Before building a database, designers often create an entity relationship diagram, or ERD. An ERD visually represents the database design. ERDs contain three elements: entities, relationships, attributes. Entities represent objects or occurrences stored in the database, usually nouns like student, faculty, or course. Relationships describe how entities interact. Common types are one-to-one, one-to-many, many-to-many. Attributes are data fields stored for each entity. Keys matter. A primary key uniquely identifies a record. A foreign key links one table to another. Section 5. Normalization and denormalization. Normalization structures data to reduce redundancy and improve integrity. It prevents insertion, update, and deletion anomalies, and is commonly used in systems where accuracy is critical, such as banking and booking systems. Denormalization combines tables to increase retrieval speed by reducing complex joins. Denormalization is common in data warehouses, where reading large volumes of data quickly matters more than frequent updates. Think: normalization equals integrity. Denormalization equals speed. Section 6. NoSQL and cloud databases. As data volumes grew, businesses began using NoSQL databases. NoSQL means non-SQL or not only SQL. NoSQL databases handle large volumes of structured and unstructured data and scale easily. Four major NoSQL types exist: key-value databases, document databases, column-oriented databases, graph databases. Key-value databases store data as pairs and are used in session management and real-time analytics. Document databases store flexible documents, often in JSON format, and are used for personalization, IoT, and real-time analytics. Column-oriented databases are efficient for analytics and reporting, but are not ideal for transaction processing. Graph databases store data as nodes and relationships. They focus on connections and use traversal algorithms. They are commonly used for fraud detection and social networks, and often work alongside relational databases. Cloud databases are hosted on cloud platforms, reduce hardware costs, support SQL and NoSQL, and are accessed through the web or APIs. Section 7. Database roles and responsibilities. Databases require specialized personnel. A database administrator, or DBA, manages performance, security, backups, and recovery. A database developer designs schemas, builds and optimizes queries, and creates reports. A system administrator manages operating systems, infrastructure, and disaster recovery. Data analysts and data scientists analyze data, find trends, create visualizations, and support decision-making. DBA responsibilities fall into 4 areas: development, operation, backup and recovery, adaptation. Section 8. Database security and recovery. Database security protects confidentiality, integrity, and availability, known as CIA. A zero-trust security model assumes no user or system is trusted until verified. There are 3 layers of database security: database level, access level, perimeter level. Database recovery relies on transaction logs. Rollback or undo recovery reverses changes from incomplete transactions. Commit or redo recovery reapplies completed transactions to restore the database to its most recent consistent state. Section 9. Data analytics. Data analytics turns raw data into insights. There are 3 types: descriptive analytics, what happened; predictive analytics, what might happen; prescriptive analytics, what should be done. Businesses increasingly rely on analytics instead of intuition. Trends include smarter, scalable AI, data-driven decision-making, growth of data products, changing roles in data science. Final wrap-up. Remember this flow. Transactions create data. Databases store data. DBMS manages data. SQL retrieves data. ERDs design data. Normalization protects integrity. NoSQL scales data. Security protects data. Analytics turns data into decisions. You're ready.